Ask any architect how the project budget got blown, and you will hear a story about scope creep or a surprise from the contractor. Ask the cost estimator, and you will hear a different story. Decisions made in design development without checking the price tag, clashes between trades that nobody coordinated, specifications written before the constructability conversation even happened. Design integration and cost control sit at the same intersection, and the exam treats them as one continuous obligation. Miss either side and you fail the exam, or worse, hand the owner a building that costs twice what it should. Here are 4 reasons this module sits where it does on the PPD exam. 4 reasons integration and cost carry this much weight. First, cost estimating gets sharper as the design develops, but only if the method matches the phase. Square foot estimates fit schematic design. Assembly estimates fit design development. And unit quantity takeoffs only work once the drawings are detailed enough to count. The exam tests whether you paired method with phase. Second, value engineering done badly strips design intent and gives the owner a worse building for less money. While done well, it asks what each component is doing and whether a cheaper alternative does the same job, and the design intent survives. The exam writes prompts where one answer is real value engineering and another is just a budget cut wearing the name. Third, constructability review happens at specific moments in the schedule. Catch a buildability problem in design development, and it's a red line. Catch it in construction documents, and it's a change order. And fourth, the CSI MasterFormat structure and disciplined design development coordination are how clashes get prevented. A mechanical chase that conflicts with a structural beam is the change order that pays for somebody's vacation, and it's the architect's job to see it first. Here are the 6 subsections in the order the module walks them. Walking the 6 subsections. 2.1 defines the architect's role at the integration and cost phase. Coordinator of consultants, steward of the budget, owner's eyes on constructability. 2.2 pairs estimating method to phase. Square foot or parametric estimates at schematic, assemblies estimates at design development, and unit quantity takeoffs at construction documents. 2.3 defines value engineering as a disciplined process, function analysis, alternatives generation, life cycle evaluation, not a panic line item cut. 2.4 covers constructability review, what the architect looks for, what the contractor brings, and the milestones where the review happens. 2.5 walks CSI MasterFormat, the 50-division structure that gives the spec a predictable shape and helps trades find their work. And 2.6 is interdisciplinary coordination during design development, the phase where structural, mechanical, electrical, and plumbing get reconciled with the architectural design before clashes become construction surprises. One posture shift before we step into section 2.1. 4 things to hold in mind. First, every cost surprise on a project was a coordination decision that could have been made earlier, and the exam tests whether you know when. The right answer is almost always the option where the decision happens in the cheapest phase to fix it. Second, the estimating method has to match the design phase. Using a square foot estimate when the design is detailed enough for an assembly's estimate gives the owner false precision, and using an assembly's estimate too early gives the owner false certainty. Third, value engineering is a process, not a list. The disciplined version asks what function each component performs and whether a cheaper alternative performs the same function, and design intent survives. The undisciplined version is just budget cuts. And fourth, constructability and coordination reviews have schedule moments. Catching a clash during design development is a red line that costs nothing. Catching the same clash during construction is a change order that costs real money. And the exam writes prompts where the timing of the catch is the point. With that posture set, we step into section 2.1. Every architect can name a project where the schematic design looked perfect on paper, and the design development phase quietly buried it. The mechanical engineer needed 16 inches of plenum, The structural engineer needed 18 inches of beam. The architect promised 24 inches of total ceiling cavity. The math did not work, and nobody owned the seam between the disciplines. Welcome to design integration, the phase where every coordination shortcut from schematic design comes due, and the phase where the public actually gets hurt when the work fails. Field fixes compromise fire ratings. Envelope details leak and grow mold. Cost overruns force value engineering of life safety systems. The ARE tests design integration and cost management because unintegrated buildings injure occupants for decades. And because you, personally, are the only professional on the project who is supposed to see the whole picture. Let me show you the 5 integration failures that map directly to real public harm patterns NCARB expects you to recognize. 5 integration failures, each one a direct line from a coordination breakdown in design development to public harm in service. Systems uncoordinated between disciplines lead to MEP clashes with structure, and the field fixes that follow compromise fire ratings and the structural integrity that took an engineer months to size. Envelope details not integrated with the structural system allow water infiltration, which produces mold, structural deterioration, and serious health hazards for the people who occupy the building. Cost overruns that arrive late force value engineering of life safety systems. Fire suppression gets downgraded, egress widths get trimmed, and occupant safety quietly diminishes. Energy systems that were never integrated with the envelope yield buildings that perform poorly and miss the sustainability targets the owner paid the architect to deliver. And constructability problems that no one caught in DD produce complex assemblies built incorrectly in the field, with performance failures that surface 5 and 10 years later. Now you can see why the exam treats design integration as a public protection issue rather than a coordination convenience. 6 reasons NCARB treats design integration as core public protection content. First, only the architect sees the whole building. Each consultant is responsible for their discipline, and the seams between them are nobody's job by default, unless the architect makes them somebody's job. Second, coordination failures that survive design development show up as change orders during construction, and change orders compress schedule and budget in ways that pressure the team to cut life safety scope. Third, hidden integration errors are the ones that cause buildings to underperform for decades. Leaking envelopes, undersized systems, premature material failures. Fourth, when value engineering is driven by cost without architect leadership, the items that get cut are the ones the contractor and owner can see least, and that often means egress, fire protection, or accessibility. Fifth, documented coordination is the architect's only defense when a claim arrives, because anything not on a coordination log effectively did not happen. And sixth, the ARE tests integration not as a coordination exercise, but as a public protection responsibility you personally carry. Let me close with the 5 takeaways that anchor this whole module. 5 takeaways from this module opener on design integration. Design integration during DD is the architect's most critical coordination responsibility on any project, and skipping it produces buildings that fail people for decades. No single consultant sees the whole picture in design development. The structural engineer sees structure, the mechanical engineer sees mechanical, the civil engineer sees civil, and only the architect is contractually obligated to see how all of those pieces fit together into one functioning whole. 5 specific integration failures map directly to public harm: uncoordinated systems, unintegrated envelope details, cost-driven life safety downgrades, missed energy targets, and ignored constructability. Hidden integration errors are the ones that injure occupants over time through leaks, system failures, and reduced safety margins. And documented coordination is the only coordination that exists from a legal and exam perspective. If it is not in a log, an RFI, or a clash report, it did not happen. Here's the uncomfortable truth most architects skip past. Schematic design and design development are not the same phase wearing different documentation hats. They answer fundamentally different questions about your building, and you confuse them at your peril. Schematic design answers what the building is, the big idea, the massing, the spatial relationships, the preliminary system types. Design development answers how the building works, how every system fits, how every connection details, how every element is sized and located in three-dimensional space. Roughly 80% of the coordination problems that hit a project in construction documentation can be traced back to the SD to DD handoff, and those problems turn into lawsuits and personal liability for the architect of record when they reach the field. Decisions left fuzzy in SD become open conflicts in DD, and conflicts left unresolved in DD become change orders in CDs. The architect who treats DD as just more drawings of the same SD ideas is the architect who fails this exam and learns about coordination the expensive way in practice. Let me show you exactly what changes between these two phases, column by column, the level of detail you owe at each step. 7 aspects, each shifting from conceptual in SD to coordinated in DD. Documentation moves from roughly 15 to 20% complete up to 30 to 50% complete, which means the design becomes legible to estimators, engineers, and builders, not just to the designer. Systems move from identified conceptually, we will use variable air volume mechanical and a moment frame structure, to defined and coordinated, with actual routes and actual member sizes that have to fit together. Materials shift from general descriptions to specific selections with manufacturer-level intent. Structure advances from a conceptual system type to sized members with a confirmed column grid that the architect has agreed to live with. MEP routes get planned in 3 dimensions with equipment sized for the loads. Cost estimating moves from order of magnitude square foot benchmarks to assemblies-based estimating with much tighter accuracy ranges. And drawings move from sketches to dimension plans, sections, and details that contractors can read. Once you understand what each phase owes, the rule for when to lock SD down becomes obvious. 6 items that must lock down before design development begins, and the architect who lets any one of them slip into DD pays for it later. Program, massing, and the major spatial relationships must be fully approved by the owner in writing, because owners who keep editing the program in DD are owners who get billed for additional services and still end up frustrated. Preliminary system types must be chosen: the structural system, the MEP system, and the envelope strategy, because those choices drive every coordination decision downstream. Floor-to-floor heights must be set with explicit plenum allowance for both structure and mechanical, because pretending you can resolve that in DD is how you end up tearing apart the section. The SD cost estimate must come in within the owner budget at the appropriate accuracy band, because launching DD over budget guarantees painful VE later. Code path must be established: occupancy classification, construction type, height and area, exit count, and accessibility. And site and zoning constraints must be confirmed against the schematic before any DD drafting begins. Walk away with these 5 takeaways, and you will treat the SD to DD handoff with the discipline it deserves. 5 takeaways from the SD to DD transition. Schematic design answers what the building is: the big idea, the spatial relationships, the system types. And design development answers how the building actually works: the sized members, the coordinated routes, the buildable details. Documentation moves from roughly 15 to 20% complete at end of SD to 30 to 50% complete at end of DD, which makes the work legible to engineers, estimators, and builders rather than only to designers. Roughly 80% of the coordination problems that hit a project later in CDs and construction can be traced back to this handoff, to SD items that were left ambiguous, and to DD conflicts that were never resolved. 6 specific items must lock before DD begins: program, system types, floor-to-floor heights, cost alignment, code path, and site and zoning. And decisions deferred from SD become open conflicts in DD, which is why disciplined architects close out SD in writing before drafting a single DD plan. Here's the trap most architects walk straight into during design development: thinking that outline specifications count as specifications. They do not, and the difference shows up the day you get sued for an installation method nobody documented. By the end of DD, you owe the owner 6 things: dimensioned floor plans, coordinated building sections, exterior elevations with material indications, preliminary wall sections, reflected ceiling plans, and outline specifications. That word outline is doing a lot of work in that list. Outline specs identify the major products and the performance criteria, but they do not yet contain the administrative procedures, the installation methods, or the section-by-section detail that contractors actually build from. Treating an outline spec as a complete spec is one of the most common traps the exam will set, because it is one of the most common errors in real practice. And the architect personally liable for the missing detail is you. The owner who signs off on DD thinking specs are done is the owner who learns at bid that the architect still has weeks of work to deliver before the project can go to market. Let me walk you through the 6 core DD deliverables and what each one contains. 6 deliverables that anchor a complete design development package. Floor plans become dimensioned layouts showing walls, doors, and major equipment with room numbers assigned, wall types identified, and door swings indicated. Building sections cut through the actual structure, showing floor-to-floor heights, structural depths, ceiling heights, and the clearances that matter to occupancy and code. Exterior elevations move from massing studies to surfaces with real material indications, fenestration patterns that match the actual window schedule, cladding types, and grade relationships that respond to the site. Wall sections start showing preliminary assembly details, insulation locations, air barrier continuity, structural connections, and reflected ceiling plans capture ceiling heights, grid layouts, and fixture locations in coordination with the mechanical equipment hung above. Outline specifications describe the major materials and systems with performance criteria and acceptable manufacturers, but stop short of the Division 01 procedures that finish later in CDs. The point that the exam returns to is the gap between outline specs and full specs. Let me make that gap explicit. 6 things that outline specifications deliberately leave out, which is why calling them complete is wrong. Division 1. The administrative and general requirements that govern how the entire project gets built is not yet drafted in DD outline specs. Detailed submittal lists, schedules of values, and procedural requirements that the contractor uses to organize the work are still placeholder level. Specific installation methods and field tolerances, which Part 3 of any CSI section spells out, are not yet specified. The full quality assurance and quality control language that tells the contractor what testing and inspection are required by section is not yet written. Substitution procedures and product approval workflows that the architect uses to evaluate or equal requests are still general. And the full Part 1, Part 2, Part 3 structure of the CSI section format is not yet populated. Outline specs name products and performance, but they do not yet read like the documents the contractor builds from. The exam will test whether you know the difference. Walk away with these 5 takeaways, and you will hand off a DD package that holds up in CDs. 5 takeaways on design development deliverables. 6 core deliverables anchor every DD package: dimensioned floor plans, coordinated building sections, exterior elevations with material indications, preliminary wall sections, reflected ceiling plans, and outline specifications. Drawings shift from the sketch and diagram quality of SD to dimensioned, coordinated documents that the team and contractor can read and reason about quantitatively. Wall sections and reflected ceiling plans appear for the first time as real deliverables in DD, not in SD, because they require sized MEP, sized structure, and locked envelope decisions that SD simply does not have. Outline specifications name products and identify performance criteria, but they stop short of the Division 01 administrative content and the Part 1 and Part 3 procedural content that complete specs require. And treating outline specs as final specs is one of the most common exam traps because it is one of the most common real practice errors. Outline is a midpoint, not a finish line. Here is the integration problem that catches more architects than any other during design development. You promised the owner 10-foot finished ceilings. The structural engineer needs 18 inches of beam depth to span the open lobby. The mechanical engineer needs 14 inches of duct depth, plus 6 inches of clearance to route supply air through the same zone. That adds up to 38 inches of structure and mechanical, plus your ceiling assembly, plus your finished floor. And your floor-to-floor was set at 12 feet 0. The math does not work, and someone is about to lose either ceiling height, beam depth, duct size, or floor-to-floor. The architect leads this coordination in DD, ensuring that structural grids align with architectural layouts, that MEP routes fit within the plenum you actually have, and that every system serves the design intent rather than fighting it. Pretending you can resolve plenum math after DD closes is how floor-to-floor heights get expensively revised in CDs. Let me walk you through the 5 most common integration issues and how disciplined architects resolve them in DD, not later. 5 integration issues, each with a predictable architectural impact and a resolution strategy that works only if you do it in DD rather than later. Structural grids that conflict with the room layout produce columns in places the program does not want them. Resolve by adjusting the grid or by accepting transfer beams and transfer slabs at premium cost. Beam depth competing with ceiling height is the classic plenum math problem. Resolve by coordinating floor-to-floor heights with the structural engineer early enough that the structure can size for the height you can afford. Large duct routes competing for plenum with beams. Resolve by establishing dedicated MEP zones and a committed plenum depth in DD, not by hoping the contractor will figure it out. Plumbing risers consume floor area on every level they pass through. Resolve by stacking wet rooms vertically and fixing riser locations in DD, because moving a riser in CDs means redrawing every floor above and below. And electrical rooms and closets have NEC required working clearances that consume real floor area. Size and locate them in DD against the code, not against optimism. 3 plenum coordination rules separate disciplined DD from the kind that produces expensive CD revisions. 6 plenum coordination rules that separate the architects who finish DD cleanly from the ones who fight it in CDs. First, sum the structural depth plus the MEP depth plus the assembly thickness before you ever approve a floor-to-floor height with the owner. Pretending the math will work out is the single most common DD coordination failure. Second, document the committed plenum depth on the building section before DD 50% review, so every discipline is sizing against the same vertical envelope. Third, lock duct routing zones in DD. Moving a duct route in CDs means rewriting the section and rerunning clash detection across the whole model. Fourth, run BIM clash detection at DD 50% and DD 95%, not just at CD start, because catching a clash in DD is order of magnitude cheaper than catching it later. Fifth, track every unresolved clash in a coordination log with a named owner and a due date. And sixth, resolve clashes in design. Never punt them to the contractor as an RFI, because RFI-driven coordination is how you transfer your liability to yourself. 5 takeaways anchor systems integration during design development. 5 takeaways on integrating structural, MEP, and architectural systems during design development. Plenum depth must sum the structural depth plus the MEP depth plus the ceiling and floor assembly. Never just one or two of those, because the others are the ones that surprise you. Insufficient plenum space is the most common DD coordination failure, on the exam and in real practice, because it requires either adding floor-to-floor height after the fact or shrinking ducts and beams against load requirements. Stack wet rooms vertically and fix plumbing riser locations in DD, because moving a riser in CDs rewrites every floor it passes. Run BIM clash detection at DD 50% and at DD 95%, not just at CD start, because earlier discovery is exponentially cheaper. And resolve clashes in design rather than punting them to the contractor as RF is. RFI-driven coordination shifts liability back to the architect even after the architect has been paid for DD. Here's the question every architect should ask before moving from DD to construction documents. Did the owner sign off in writing on the DD set? If the answer is anything other than yes, you have a problem. AIAB 101, Article 3.3 requires owner approval at the end of every phase before you begin the next one. And that is not bureaucratic theater. It is the moment that you and the owner agree on scope, quality, and budget alignment for what is about to get drafted as construction documents. Skip it, and you are personally exposed when the owner later claims the building you drew was not the building they approved. The exam tests this directly. Owners who never sign DD approval are owners who can sue the architect for misalignment, and architects who never demand it lose those lawsuits. Documented written approval is not optional. It is the architect's primary defense against scope creep claims and budget shock disputes during construction. Let me walk you through the 4 coordination checkpoints that surround the formal approval and what each one tests. 4 coordination checkpoints surround the formal DD approval, and the architect is responsible for running all of them. Interdisciplinary coordination brings together the architect, the structural engineer, and the MEP engineers to resolve spatial conflicts between systems. This is where the plenum math gets reconciled and the column grid gets locked. Code review brings together the architect and the code consultant to verify zoning compliance, building code compliance, and accessibility against the more detailed DD design. Owner progress meetings bring together the architect, the owner, and possibly the construction manager to confirm the design direction is still consistent with the owner project requirements and to review the working budget. And cost estimate review brings together the architect, the cost estimator, and the owner to compare the updated DD estimate to the project budget and to identify any value engineering needs early enough that they can be designed rather than cut. 5 milestones structure the DD approval cycle so that nothing falls through the cracks. 5 milestones that structure a defensible DD approval cycle. DD kickoff is the moment you confirm with the owner that all SD decisions are locked and the project scope is frozen. This is when you put any remaining SD level ambiguity in writing and get it resolved before the team starts drafting DD. Mid-DD review is the systems coordination checkpoint at roughly 50% DD, with a preliminary cost update so any drift surfaces while change is still cheap. DD completion involves a full package review of plans, elevations, sections, and outline specifications with all consultants represented. Owner written approval is required before proceeding to the CD phase per AIAB 101. And that approval is what you point to in a deposition if the owner later claims the building was not what they expected. And budget reconciliation closes the loop, comparing the updated DD estimate to the project budget and triggering VE if the gap is too wide to close in CDs. 5 takeaways anchor owner approval and coordination checkpoints during DD. 5 takeaways on owner approvals and coordination checkpoints during design development. Owner written sign-off on the DD set is required by AIAB 101, Article 3.3, before you can proceed to construction documents. This is contractual, not procedural. Skipping DD approval is direct architect liability exposure, because without it, the owner can later claim the project they approved is not the project you drew. 4. Coordination checkpoints surround the formal approval. Interdisciplinary coordination, code review, owner progress meetings, and cost estimate review. And the architect is responsible for running all of them. Mid-DD review at roughly 50% catches design drift and budget drift while change is still cheap to make, before the team has spent weeks drafting against the wrong assumptions. And budget reconciliation at DD completion triggers value engineering before CD phase starts, because launching CD over budget guarantees painful late-stage cuts to scope, quality, or schedule. Here's the cost estimating mistake most architects make at least once in their career, and the exam loves to test it: applying the wrong estimating method at the wrong phase of design. You cannot do a detailed unit cost estimate in programming because there is nothing to measure, and you have no business using an order of magnitude square foot estimate at design development, because by then you have enough detail to do real assemblies-based work. And sloppy estimating at DD is how you launch CDs quietly over budget. Cost estimating is not one technique. It is 4 different techniques matched to 4 different phases, each calibrated to the information available at that point in design. Precision grows with information, not with owner pressure. The architect who quotes a hard number at SD without disclosing the plus or minus 25% range is the architect who gets sued when bids come in 20% high. And the exam will fail you on a question that hands you a phase mismatched estimate if you do not flag it as the trap. Let me walk you through the 4 methods, the phase they fit, and the accuracy you can honestly promise at each step. 4 methods, 4 phases, 4 accuracy ranges, and you must know which pairs with which. Order of magnitude estimating uses high-level benchmarks like dollars per bed for hospitals or dollars per parking stall for garages. It is appropriate at programming and pre-design only, when you have almost nothing concrete, and it carries an accuracy range of plus or minus 25 to 30%. Square foot or parametric estimating uses published cost data from RS Means or Marshall and Swift, adjusted for building type, quality, and location. It fits schematic design, with accuracy plus or minus 15 to 20%. Assemblies estimating using the uniformat structure: substructure, shell, interiors, services, equipment, site work. Fits design development, where you have enough detail to price building systems but not individual items, with accuracy plus or minus 10 to 15%. And detailed unit cost estimating, organized by the MasterFormat divisions, is the construction document method, where every line item gets priced against unit costs, with accuracy plus or minus 5 to 10%. NCARB updated the April 2026 PPD objectives in a way that changes how you should study this content. 6 points that reflect the April 2026 NCARB objective updates for PPD cost estimating. Objective 5.2 used to read, develop a project cost estimate. It now reads, evaluate cost estimates based on the project design, which means the exam is shifting toward review and judgment questions rather than build the estimate from 0 questions. Objective 5.3 used to focus on evaluating design alternatives. It now reads, evaluate the project design holistically based on cost, which broadens the test from local trade-offs to whole design judgment. Practically, expect questions that present an estimate and ask whether it is appropriate, accurate, or correctly bounded for the phase. Know the accuracy ranges cold, plus or minus 25 to 30 at programming, 15 to 20 at SD, 10 to 15 at DD, 5 to 10 at CDs. Know which method is wrong for a phase, not just which is right. Order of magnitude at DD and detailed unit cost at SD are both classic tested traps, and recognizing them on site is how you score points. Walk away with these 5 takeaways, and you will pass the cost method matching questions cleanly. 5 takeaways on cost estimating methods by phase. 4 methods map to 4 phases: order of magnitude to programming, square foot or parametric to SD, assemblies to DD, and detailed unit cost to CDs, and the exam will punish you if you swap them. Accuracy ranges tighten as design information grows, from plus or minus 30% at the start to plus or minus 5% at the end, and you must disclose the range honestly to the owner. Order of magnitude estimating at design development is a tested exam trap because by DD you have enough detail to do better, and using a sloppier method is a professional failure the exam treats as an architect liability issue. Detailed unit cost estimating at schematic design is the symmetric trap. There is nothing to count at SD, so the precision is fake. And the April 2026 objective shift moves the exam from develop the estimate toward evaluate the estimate, which means you need to recognize when a presented estimate is wrong for the phase, not just produce one of your own. Here is the square foot estimating mistake the exam loves to test. Pulling a number out of RS means at $375 per square foot and quoting it to the owner without a single adjustment for where you are building, when you are building, or what you are actually building. Most architects do this at least once. The ones who do it once also get sued or fired for it once because the number that came out of the published data was the national average benchmark, and your project is not in the national average. It is in San Francisco, where labor runs 40% above the median, or in $2,026, while the data is in $2,023, or with a curtain wall ratio twice the parametric assumption. Square foot data must be adjusted for location with the city cost index, adjusted for time with escalation factors, and adjusted for project-specific conditions like site difficulty, quality level, and program complexity. If you skip the adjustments, your estimate is fiction, and you will personally absorb the gap. Let me walk you through the 4 adjustment categories every honest square foot estimate has to apply. 4 adjustments every defensible square foot estimate has to apply. Location adjustment uses the RS means city cost index because labor and material costs vary by 30 to 50% between cities. A project in Manhattan is not priced like a project in Topeka, and pretending otherwise is malpractice. Time adjustment uses engineering news record indexes, or RS means escalation factors, because costs rise 3 to 8% per year, and data more than 12 months old needs explicit forward projection or backward adjustment depending on when the project is bidding. Quality level adjustment uses the Marshall and Swift classification system because a Class A office building costs 40% more than a Class C building of the same size, and that is real money. And site and program complexity adjustment is architect judgment supplemented by contractor input. Difficult urban sites with constrained logistics, complex programs with extensive specialty space, and tight schedules all add cost the parametric tables do not capture. Parametric estimating extends the square foot method by adding building parameters as cost drivers. 6 parametric drivers that move cost in ways simple dollars per square foot does not capture. Perimeter, the exterior wall area, drives the skin cost and the operating energy cost because more perimeter means more cladding, more flashing, more thermal bridging, and more heat loss. Floor area is the obvious one. Total enclosed square footage drives structural quantities and MEP system sizing. Number of floors drives vertical transportation cost because each additional floor adds elevator capacity and stair count, often disproportionately to area. Floor-to-floor height drives skin cost. Taller floors mean more square feet of cladding for the same plan area, and drives MEP cost because larger plenums and longer ducts cost more. Window-to-wall ratio is the single biggest skin cost driver in many buildings because curtain wall costs 3 to 5 times what an opaque wall costs, and energy performance shifts dramatically. And program mix drives total cost because specialty spaces like labs, surgical suites, or commercial kitchens carry premiums that must be quantified and added to the base square foot number. Walk away with these 5 takeaways, and you will adjust every square foot estimate before you ever quote it to an owner. 5 takeaways on square foot costs and parametric estimating. National average data needs location, time, and quality adjustment before it is quotable to an owner, and the exam will test whether you know to apply all 3. The RS means City Cost Index is the standard tool for the location adjustment, swinging the base number by 30 to 50% depending on geography, and forgetting it on a high-cost city is one of the most painful mistakes a young architect makes. Engineering news record indexes handle the time escalation adjustment because construction costs rise 3 to 8% per year, and using a base year more than 12 months stale without escalation understates real cost. Parametric drivers, perimeter, floor area, number of floors, floor-to-floor height, window-to-wall ratio, and program mix extend basic square foot estimating to capture cost movement that simple total area methods miss. And skipping the adjustments transfers the cost gap directly to the architect, who personally absorbs the difference when bids come in higher than the unadjusted estimate. Here is the contingency principle that catches most architects on the exam and in practice. Contingency must decrease as design progresses because the unknowns are supposed to be getting smaller. You start at schematic design with a 15% design contingency because so much is undefined. By design development, it should drop to 10%. By construction documents, it should drop to 5 or 7%. If your contingency is the same number at CDs as it was at SD, you are quietly admitting that you have not actually resolved the unknowns. You have just kept padding the estimate to cover your uncertainty. The owner who sees that pattern stops trusting the estimate, and the exam will fail you on a question that asks how design contingency should change between phases if you answer that it stays flat. Cost escalation also keeps pressure on the number from the outside. So the architect who fails to budget for both shrinking contingency and growing time-driven cost is the architect who gets sued when bids return over budget. Let me walk you through how contingency should change phase by phase and how escalation gets calculated. 5 phases of design, 5 contingency bands, and you must know the pattern. Programming and pre-design carry a design contingency of 20 to 25% because almost nothing is defined yet and the unknowns are large. Schematic design drops to 15 to 20% because systems are identified, even if not yet coordinated. Design development drops further to 10 to 15% because systems are coordinated and materials are selected, and the architect now knows much more about what the building actually is. Construction documents drop to 5 to 7% because every line is drawn, every product is specified, and the remaining unknowns are limited to field conditions and contractor judgment. And during construction itself, the owner holds a separate 3 to 5% change order contingency for genuine, unforeseen conditions and approved scope changes. A team that keeps contingency flat across phases is a team that is not actually reducing risk through design, and the exam will mark that as wrong. Escalation calculation runs on top of the contingency math. Let me show you the inputs. 6 inputs that make an escalation calculation defensible. The base estimate date is when the unit costs were priced, and this is the anchor for everything else. The midpoint of construction is when most of the cost is actually being spent, not when the project starts and not when it ends. The annual escalation rate is typically 3 to 8% per engineering news record indexes, but you should match the rate to the specific building type and location because residential and healthcare escalate differently. You compound the rate across the number of years between the base estimate date and the midpoint of construction, not simple addition, compound multiplication. You add escalation to the base estimate as a separate identified line item, not buried in the unit costs because the owner needs to see it explicitly to plan financing. And you distinguish design contingency from construction contingency in the documentation. They cover different risks, they belong to different parties, and conflating them confuses the owner and weakens your position when scope changes arrive. Walk away with these 5 takeaways, and you will defend any contingency and escalation question the exam throws. 5 takeaways on cost escalation and contingency. Design contingency must shrink as design progresses, from 20 to 25% at programming, down to 5 to 7% at construction documents. And that shrinkage is how you demonstrate that you are reducing risk through design rather than hiding it. Flat contingency across phases signals to the owner and to the exam that you have not actually resolved the unknowns, and it is treated as an architect failure to manage risk. Escalation projects current dollar costs forward to the midpoint of construction, not to the project start or the project end, because the midpoint is when most of the spend actually happens. You compound the annual escalation rate across years, never simple multiplication of 1 year times the rate, because compounding captures the real way prices rise. And you keep design contingency and construction contingency as separate identified line items, because they cover different risks held by different parties, and you defend them differently in disputes. Here is the cost language trap most architects fall into the first time they talk to a developer or an institutional owner. You proudly quote a construction cost estimate of $45 million. The owner says the project budget is $52 million. You think you are $7 million under, and the owner thinks you are $5 million over, because their $52 million is the total project cost, while your $45 million is only the hard cost construction piece. Project cost is not construction cost. The architect's estimate typically covers the hard costs, the actual cost of building the building, and explicitly excludes the soft costs, the land, and the financing that the owner must fund separately. The exam tests this distinction directly. When a question says project cost, it includes soft costs, and when it says construction cost, it does not. The architect who quotes project cost as if it were construction cost is the architect who gets sued for malpractice when the financing closing reveals the gap, because the owner relied on the wrong number to size their loan. Let me walk you through the 4 categories of project cost and which one the architect actually estimates. 4 categories make up total project cost, and only one of them is the architect's number. Hard costs are the actual cost of building the building: labor, materials, equipment, and the contractor's overhead and profit. And that is what the architect's estimate covers. Soft costs are everything that is not physical construction: architectural and engineering fees, permits, testing and inspection, furniture and fixtures and equipment outside the contract, legal fees, insurance, and project management staff. The architect typically gives input on soft costs, but does not own the number. The owner does. Land cost is the owner's responsibility entirely: acquisition, closing, title work, environmental remediation if needed, and the architect should not be quoting it. Financing cost is also the owner's number: construction loan interest, origination fees, and the carrying costs through development, and it can run 10 to 15% of total project cost on a leveraged deal. Total project cost is the sum of all 4, and only the owner can produce that number. Soft costs deserve a closer look because they trip up architects who think their estimate covers them. 6 common soft cost categories that the architect's hard cost estimate explicitly excludes. A&E fees, meaning the architect plus every consultant on the design team, are a soft cost, even though architects sometimes confuse themselves about that. Permits, plan review fees, and utility connection charges are soft costs, paid by the owner to authorities having jurisdiction. Geotechnical investigations, environmental assessments, and surveying are testing and inspection soft costs paid by the owner. FFE, furniture, fixtures, and equipment, is a soft cost only when it is outside the construction contract, which is the typical convention. If FFE is in the contract, it becomes a hard cost. Legal fees, owner insurance like OCIP or CCIP programs, and the owner's project management staff are all soft costs. And the owner reserves their own project contingency separately from the construction contingency the architect carries, because the owner's contingency covers soft cost surprises and design changes the architect cannot anticipate. Walk away with these 5 takeaways, and you will never confuse construction cost with project cost again. 5 takeaways on hard versus soft costs. The architect estimates hard costs only, the physical construction cost of the building, including labor, materials, equipment, and contractor overhead and profit, and that is the only number the architect should quote without disclosing soft and other costs separately. Soft costs include A&E fees, permits, testing, FFE outside the contract, legal, insurance, and owner project management. And the architect provides input, but the owner owns the soft cost line. Land and financing are owner-only categories that the architect should never be quoting, because the architect has no role in acquiring land or negotiating construction loans. Project cost equals hard plus soft plus land plus financing. It is always larger than construction cost, usually by 20 to 40% depending on the project. And quoting project cost as if it were construction cost is malpractice, because it sets the owner up to discover the gap at financing closing rather than during design, and that conversation ends careers. Here is the value engineering distinction the exam will fail you on if you miss it, and the distinction that gets architects sued in practice. Value engineering is not the same thing as cutting cost. VE is a systematic method that asks one question: can we deliver the same function at lower total cost without sacrificing quality, performance, or reliability? Cost-cutting deletes the function. VE preserves it. You can switch from stone veneer to precast with a stone aggregate finish, and that is VE, because the function of weather protection and architectural expression is preserved. You cannot delete the lobby waterproofing membrane and call it VE, because the function of keeping water out is gone, and the owner who finds out 3 years later when the slab is rotting has a lawsuit waiting for the architect who signed off on it. 4 concepts define VE rigorously: function, value, the VE goal, and what is not VE. 4 concepts you must hold straight. Function is what the assembly does, described as a verb plus a noun. Support load, enclose space, control climate, resist moisture. The verb-noun discipline forces you to name the function before you discuss the product, and naming the function is what separates VE from arbitrary scope cuts. Value is the ratio of function to cost. Higher value means the same function for less cost or more function for the same cost. The VE goal is to maintain or improve function while reducing cost, which is why switching from stone veneer to precast with a stone aggregate finish counts as VE. Same weather protection, same architectural intent, lower cost. And the negative case: anything that reduces function to save money is not VE. Removing insulation, deleting waterproofing, eliminating a fire-rated assembly. Those are scope deletions, and the exam treats them as architect malpractice when the architect labels them as VE. Walk away with these 4 takeaways, and you will never call a scope deletion a VE proposal. 4 takeaways on the VE definition. Value engineering preserves function. That is the single defining test, and every exam question on VE hinges on whether the proposal keeps the function or deletes it. Value is the ratio of function to cost, which means you can increase value either by lowering cost while holding function steady, or by holding cost steady while improving function. Both moves count. VE substitutes means not ends. The building must still do what it was supposed to do, just through a different assembly. Deleting scope to save money is cost-cutting, not VE, and labeling a scope deletion as VE on a real project is the kind of paperwork that turns into a deposition exhibit and personal liability exposure when the tenant injury claim lands. Here is what separates a legitimate value engineering study from a panic-driven cost-cutting meeting in a conference room. You must follow the 5-phase job plan, every time in order. A real VE study has structure, information, creative speculation, evaluation, development, presentation, and each phase produces a specific output that feeds the next. The architect who walks into a VE meeting and starts proposing substitutions before the information phase is the architect who recommends the wrong substitution, gets the owner sued by an end user, and personally absorbs the redesign cost. On federal and many public projects, VE studies must follow ASTME 1699, the standard practice for performing value analysis of buildings and building systems, which formalizes the same 5-phase plan. If you skip a phase, the result is not VE. It is an arbitrary scope cut wearing a VE label, and the exam will mark it wrong. Let me walk you through the 5 phases and what each one is supposed to produce. 5 phases, 5 outputs, 1 key question per phase. The information phase gathers data, what the system does, what it costs, what the constraints are, and the answer to what does it do becomes the function statement that anchors the rest of the study. The creative or speculation phase brainstorms alternatives without judgment, which means no shooting down ideas, no premature cost screening, quantity over quality, because the cheap idea you reject in minute 2 is sometimes the one that solves the problem in minute 30. The evaluation phase screens alternatives for feasibility and ranks them by value, killing the ideas that violate code or fail constructability, and ordering the survivors. The development phase builds detailed cost-benefit analyses on the top alternatives, because the exam-wrong answer is to recommend an idea before it has been costed. And the presentation phase delivers the recommendations to the owner with documented rationale. The VE team does not unilaterally implement. The owner decides. Strategies that actually move the number tend to cluster around 5 building systems. 5 strategy clusters that actually move the cost number on real projects. Structure is the first, switching between steel and concrete based on local market conditions because labor and material costs vary by region, and one system is usually meaningfully cheaper in any given market. Envelope is the second, substituting a full curtain wall with a window wall or storefront system, which can cut envelope costs by 20 to 30% if the architectural intent allows. MEP is the third, right-sizing equipment instead of oversizing the safety margin and adding heat recovery components that pay back operating cost. Interior is the fourth, reducing corridor ceiling height to gain plenum space, using standard door sizes instead of custom, and selecting finished products with similar performance at lower unit cost. And site is the fifth, minimizing excavation and balancing cut and fill, because earthwork is one of the few cost categories where small grading changes produce 6-figure savings without affecting the building at all. Strategies in any other category usually delete function, and you are back to cost cutting. Walk away with these 4 takeaways, and you will know what a real VE study looks like. 5 takeaways that anchor the VE process. The 5 phases are information, creative or speculation, evaluation, development, and presentation, and they must run in order because each phase produces the input for the next. The function statement built during the information phase anchors every legitimate VE study. Without it, the team is just trading opinions about which line items look expensive. SDEM 1699 governs VE on federal and most public projects, and the exam expects you to recognize the standard by name. Skip a phase and the result is not VE. It is a list of arbitrary cuts wearing a VE label, and the architect who signs off on it without challenge faces the lawsuit when the cuts cause downstream harm. And the VE team recommends. The owner decides. The architect who confuses recommendation with authority oversteps the role and takes on personal liability for unauthorized scope reduction. Here is the VE timing rule the exam will hand you in a scenario question. VE effectiveness decays as the design progresses, and the cost to implement VE changes climbs in the opposite direction. VE at programming is almost free, because the team is still trading ideas on paper and no commitments have been made. VE at construction documents is a redesign event. Drawings get reissued, specs get rewritten, consultants bill, and the schedule slips. VE during construction is a contractor-initiated value engineering change proposal, or VECP, which can save money but typically comes with delay claims and warranty disputes attached. You will face exam questions that ask when to run VE and what the trade-off is. And the wrong answer is always to defer VE to a later phase because nobody had time earlier. The architect who defers VE is the architect who personally absorbs the redesign cost when the owner files a malpractice claim for the operating shortfall. Let me walk you through VE effectiveness phase by phase and what the schedule impact looks like. 5 phases, 5 effectiveness levels, 5 schedule impact bands. Programming is the highest yield moment for VE because fundamental decisions about size, program, and basic system type are still open. Schedule impact is minimal because nothing has been drawn yet. Schematic design is the second highest yield point because system types can still change cleanly. You can switch from steel to concrete or from VAV to VRF without throwing away significant work. Design development is moderate yield because by DD the systems are chosen and you can only refine within them. And schedule impact is moderate because consultants have to revise their work. Construction documents is low yield. Changes require significant rework. Every drawing gets reissued and the schedule slips noticeably. And during construction, VE happens through Contractor Value Engineering Change Proposals, VECPs, which can save money but typically introduce schedule delays, claim exposure, and warranty disagreements that erase part of the savings. Beyond timing, the exam loves to test whether you can tell a real VE proposal from a cost-cutting deletion. 5 paired examples that the exam tests directly. Real VE preserves required function. Cost-cutting reduces or eliminates function, and that is the single sharpest dividing line. Real VE uses systematic analysis of alternatives with a documented job plan. Cost-cutting picks line items at random because they look expensive on a spreadsheet. Switching to tilt-up concrete from precast is VE if the structural function is preserved. Eliminating the lobby waterproofing membrane to save money is cost-cutting because the function of keeping water out is gone, and the owner will be sued by tenants when the slab fails. Using geothermal instead of a boiler chiller is VE if the HVAC function is preserved at lower lifecycle cost. Deleting half the landscape budget is cost-cutting because the function of stormwater management and site cooling is reduced. Real VE maintains quality and performance. Cost-cutting sacrifices them. And the exam will give you a question where a proposal sounds like VE, but actually deletes the function, and you have to recognize the trap. Walk away with these 4 takeaways, and you will defend any VE versus cost-cutting question the exam throws. 5 takeaways on VE timing and the cost-cutting distinction. VE effectiveness drops as design progresses, which means programming and SD are the highest yield moments for the exercise, and CDs are the lowest. The earliest VE is the cheapest VE, and architects who defer VE to a later phase to avoid the conversation now absorb the redesign cost later when the owner discovers the budget gap and triggers personal liability. VE preserves function, cost-cutting deletes it, and that is the defining test the exam will hand you. A scope deletion labeled as VE is malpractice exposure because the architect who endorses a deletion as a VE recommendation has signed a document that the plaintiff lawyer will read aloud in deposition. And VE during construction, through contractor VECP proposals, carries delay and claim risk that often erases part of the savings. So the smart move is to run real VE earlier and let construction phase VE be the exception rather than the strategy. Here is the constructability question every architect must answer before the drawings leave the office. Can the building you have drawn actually be built? With the labor that exists in this market? With the tools that crew has? Within the tolerances those materials and trades can hold? Constructability is the degree to which the design facilitates the actual physical work of construction, and it is judged against 6 principles: standard sizes, minimal material variety, real tolerances, sequencing, practical connections, and weather realism. The architect who designs custom one-off steel connections to save weight, then learns the local fabricator cannot produce them on schedule, is the architect personally explaining the 6-week delay to the owner. The architect who specifies wet masonry work in January in Minnesota and assumes the contractor will figure it out is the architect whose firm gets sued for the temporary enclosure cost. Constructability is not a contractor's problem. It is your problem, and the exam treats it that way. Let me show you what good and poor constructability look like in 5 direct paired examples. 5 paired examples that the exam tests by sight. Standard steel connections are good constructability. The fabricator already has the details on the shop floor, the welder already has the procedure qualified, and the inspector already knows what to look for. Custom one-off connections require shop drawings, special inspection, and weld procedure qualifications that add weeks to the schedule. Repetitive floor plans are good constructability. The crew develops a rhythm by floor 3, and the per-floor cost drops. Every floor being different is poor constructability because the crew restarts the learning curve on every level. Modular 4-foot dimensions are good because sheet goods, framing members, and most components come in standard 4-foot increments. Odd dimensions require custom cuts that waste material and labor. Accessible work areas for cranes and equipment are good constructability. Tight urban sites with no crane access force costly small equipment workarounds and schedule extensions. Simple waterproofing details are good. Complex intersecting roof geometries are where leaks live, and the architect who designed them is the architect whose insurance carrier pays for the remediation when the building leaks. Walk away with these 4 takeaways, and constructability becomes a design discipline, not an afterthought. 4 takeaways on constructability. Constructability is the yes or no question of whether the design can be built efficiently, safely, within budget, and within schedule. And the answer must be yes before the documents leave the office. 6 principles govern the test: standard sizes, minimal material variety, real construction tolerances, sequencing, practical connections, and weather and seasonal realism. Poor constructability is an architect liability issue, not a contractor problem, because the architect is the only party that controls the design at the moment constructability is determined. Custom design is expensive unless function demands it. Every custom connection, every odd dimension, every complex roof geometry has to earn its cost premium in the design rationale, and the exam treats unjustified custom work as architect error. And the practical rule that summarizes the discipline? Design with the crew, the tools, and the tolerances in mind, because the building gets built by humans with real constraints, not by the perfect contractor in the architect's imagination. Constructability reviews should run at every design phase, but design development is the cheapest checkpoint on the entire project. The reason is simple. By DD, enough design detail exists to identify real problems. You can see the structural to envelope interface. You can measure plenum depth. You can read the door schedule against the wall types. But the design is still flexible enough to fix those problems without massive rework, because nothing has been bid and the documents have not been issued. Wait until CDs and every fix costs 3 to 5 times more because every drawing gets reissued and every consultant rebills. Wait until construction and the fix is a change order, a delay claim, and sometimes an injury when a worker tries to install the impossible. The architect who runs a serious DD constructability review is the architect who avoids the lawsuit. The architect who skips it is the architect who explains the change orders to the owner under oath. Let me show you the 6 constructability issues that hit hardest when caught late. 6 constructability issues that the exam expects you to recognize on site, ordered by how often they hit on real projects. Insufficient clearances is the first. The crew cannot route mechanical ductwork around the structural beams the way the drawings show, and the fix is either redesign or beam modification and a delay. No crane access is the second. Large precast panels physically cannot reach the site on an urban or constrained lot, and the fix is logistics gymnastics that costs 6 figures. Non-standard sizes is the third. Custom window sizes cost roughly 3 times standard sizes, and the architect who specified them without justification absorbs the budget overrun or the redesign request. Conflicting tolerances is the fourth. Steel framing holds a 1/4 inch tolerance, while curtain wall holds an 1/8, and the joint between them needs field modification on every project where the architect failed to design the tolerance transition. Wet work in winter is the fifth. Masonry, scheduled for January in a northern climate, requires temporary enclosures and heated curing, which add weeks and dollars. And sequencing conflicts is the sixth. Interior finishes scheduled before the building is watertight is the kind of mistake that turns into water damage, mold remediation, and a lawsuit from the owner. Walk away with these 4 takeaways, and your DD reviews catch what matters. 4 takeaways on constructability review timing. DD is the cheapest place to catch constructability errors because the design has enough detail to spot them and enough flexibility to fix them without throwing away significant work. Field experience belongs on the review team. A constructability review without someone who has actually built something is a review by people who only know what drawings look like, and the exam expects you to recognize that gap. The review must cover clearances, tolerances, sequencing, and weather, not just the obvious geometric clashes, because the expensive errors live in the seams between disciplines and seasons. Late discovery cost grows roughly 10-fold per phase. A DD fix that costs $10,000 becomes a CD fix at $100,000, and a construction fix at $1 million. And skipping the DD review is malpractice exposure, because the architect who issued documents without a constructability check is the architect named in the resulting claim when the building cannot be built as drawn. Here is the delivery method rule that drives constructability outcomes, and you must hold it straight on the exam. The moment the contractor enters the project is the moment field experience enters the design, and that moment is set by the delivery method the owner chose. In design, bid, build, the contractor is not selected until the documents are complete, which means the architect carries the constructability burden alone through every phase. And the historical record on DBB shows higher change order rates and more lawsuits because no one with a hammer reviewed the drawings before they were bid. In CMAR, the construction manager joins during schematic or design development as an advisor, bringing constructability and cost feedback while the design can still respond. In design build, the designer and builder share a single team from day one. In IPD, every party shares risk and reward from programming onward. The exam will fail you on a question where the right answer hinges on which delivery method is in play if you quote DBB constructability advice for an IPD project. Let me walk you through the 4 delivery methods and what each one means for constructability. 4 delivery methods, 4 constructability benefit levels. Design, bid, build is the traditional method. The contractor is not selected until the construction documents are complete, which means there is no field input during design, and constructability is entirely the architect's responsibility. The historical record on DBB shows higher change order rates and more disputes because problems that a contractor would have flagged at DD get discovered in the field instead. CM at risk brings the construction manager in during schematic design or design development as an advisor on cost and constructability, and the architect benefits from real-time market pricing and field judgment while the design can still change. Design build puts the designer and builder on the same team from the start, which means constructability is built into the design process by definition, though it changes the architect's contractual role significantly. An integrated project delivery is the highest collaboration model. All parties collaborate from programming onward with shared risk and reward, which drives early problem solving and produces the lowest change order rates, though it requires the owner to commit to a multi-party agreement. When the CM is in the room during DD, here's what they actually contribute. 6 concrete contributions a CMAR brings to design development that the architect cannot easily produce alone. Preliminary cost estimates from current market pricing, not from RS means or 2-year-old published data, but from the bids that came back on similar projects this quarter in this market. Constructability review of structural and envelope details, with the perspective of the trades who will install them. Identification of long lead items requiring early procurement, switchgear, custom storefront, specialty equipment, which the architect can otherwise miss until the schedule is in trouble. Labor availability assessment for proposed building systems, because a beautiful VRF design fails if there are no certified VRF installers within 2 hours of the site. Phasing and logistics planning for constrained sites, including crane locations, laydown areas, and site access. And subcontractor market feedback on the proposed assemblies. Which products are being delivered on time? Which fabricators have backlogs? And which trades are over capacity in this region? The architect on a DBB project must source this information independently or fly blind. Walk away with these 4 takeaways and your delivery method questions resolve cleanly. 4 takeaways on delivery methods and constructability. Delivery method sets when contractor input arrives in the design, and the answer to the exam question hinges on which method the scenario describes. In design bid build, the architect carries the constructability burden alone, with no contractor in the room until the documents are bid, and the architect is the only professional accountable for whether the design can actually be built. In CMR and IPD, the contractor is in the room during design development, which dramatically improves constructability and reduces change orders downstream. DBB carries higher historical change order rates than the early contractor involvement models, and the exam treats that as a known statistical pattern you should be able to explain. And the practical rule? Match the constructability strategy to the delivery method. The architect who runs an IPD constructability process on a DBB project wastes the owner's time. The architect who runs a DBB process on an IPD project wastes the opportunity and gets the question wrong on the exam. Here is the spec organization rule the exam tests on every PPD attempt. MasterFormat is the language the construction industry uses to organize everything that goes into a building, and you must know the structure cold. MasterFormat, published by the Construction Specifications Institute, organizes construction information into 50 divisions grouped into 5 categories. Subcontractors bid by division. Suppliers sell by division. Estimators cost by division. The architect who routes information to the wrong division is the architect whose bid documents come back with RF is on day 1 and missing scope on day 30. You will see exam questions that test whether you know which division covers which work. Concrete is Division 3. Metals is Division 5. Thermal and moisture protection is Division 7. Openings is Division 8. HVAC is Division 23. And you must answer without looking them up. Get the divisions wrong on a real project, and the contractor builds the wrong scope, the owner sues for the missing work, and the architect's E&O insurance pays the gap. Let me walk you through the 5 division groups so the 50 numbers stop feeling random. 5 division groups that organize the 50 MasterFormat divisions logically. General requirements is Division 1 alone, and it covers the administrative and procedural requirements, submittals, quality control, temporary facilities, project meetings, that apply across every other division on the project. Facility construction is divisions 2 through 14, and it covers the building itself, existing conditions, concrete, masonry, metals, wood and composites, thermal and moisture protection, openings, finishes, specialties, equipment, furnishings, special construction, and conveying equipment like elevators. Facility services is divisions 21 through 28, and it covers fire suppression, plumbing, HVAC, integrated automation, electrical, communications, electronic safety and security, and integrated fuel systems, the MEP and life safety systems that make the building work. Site and infrastructure is divisions 31 through 35, and it covers earthwork, exterior improvements, utilities, waterways and marine, everything outside the building footprint. And process equipment is divisions 40 through 48, used on industrial projects for material handling, water and waste treatment, and pollution control. On most commercial projects, you live in the first 4 groups and never touch the 5th. Walk away with these 4 takeaways, and you will route any spec call to the right division. 4 takeaways on MasterFormat. MasterFormat is the industry's shared spec vocabulary. Every architect, contractor, supplier, and estimator organizes their work by these divisions, which is why you must know the structure cold. The 50 divisions are arranged in 5 logical groups: general requirements, facility construction, facility services, site and infrastructure, and process equipment. And once you see the grouping, the numbers stop feeling random. Misrouted specs trigger RFIs at minimum and missing scope at worst. And a project that gets bid with scope landed in the wrong divisions comes back with proposals that miss the work entirely. Memorize the 7 most tested divisions. Division 1 for general requirements, 3 for concrete, 5 for metals, 7 for thermal and moisture, 8 for openings, 9 for finishes, and 23 for HVAC. And the exam questions on division numbering resolve themselves. And the consequence? A wrong division spec call is malpractice exposure, because the architect is the only professional accountable for the organization of the construction documents, and the owner who sues for missing scope traces the issue back to the spec author. Here is the spec type principle the exam tests directly, and the principle that decides who pays when something fails on a real project. The type of specification you write determines who carries the performance risk. A prescriptive specification tells the contractor exactly what to install: the materials, the dimensions, the chemical composition, and the architect, having chosen the exact product and method, carries the performance risk. If the product underperforms, the architect is the one who selected it. A performance specification tells the contractor what the result must achieve: the strength, the thermal value, the sound rating, and lets the contractor select the means to get there, which shifts the performance risk to the contractor. A proprietary specification names a specific product and manufacturer, which guarantees the exact match the architect wants, but may violate competitive bidding on public projects. The architect who picks the wrong spec type carries liability they never meant to take. And the exam will hand you a fact pattern where the right answer hinges on who owns the performance. Let me walk you through the 3 types side by side. 3 spec types, 3 risk profiles. Prescriptive specifications, sometimes called descriptive, tell the contractor exactly what to install. ASTMC 216 grade SW type FBS brick with a minimum compressive strength of 3,000 pounds per square inch. And the advantage is that the spec is clear and enforceable, with no ambiguity for the contractor to exploit. The risk is that the architect, having chosen the exact product, carries the performance risk if the product underperforms. Performance specifications define the required outcome. Curtain wall shall achieve a U value of 0.28 or better, and an STC rating of 35 minimum, without dictating how to get there, which allows contractor innovation and transfers performance risk to the contractor. The downside is that performance specs are harder to enforce because the test criteria must be precisely written and verifiable. Proprietary specifications name a specific product by manufacturer and model. Acme Model 3500 Series Window, no substitutions, which guarantees the architect gets the exact product specified, but may violate competitive bidding rules on public projects unless the spec includes or approved equal language. Exam-ready examples make the three types unmistakable on a test question. 5 exam-ready examples that lock the 3 spec types. Prescriptive. Brick shall be ASTMC 216, grade SW, type FBS, with minimum compressive strength of 3,000 pounds per square inch. Notice that every dimension and property is named, and the contractor's only freedom is choosing among brands that meet that exact spec. Performance. Curtain wall system shall achieve a U value of 0.28 or better and an STC rating of 35 minimum. Notice that no product is named, only the result, with the contractor free to choose how to achieve it. Proprietary closed. Provide Acme Model 3500 Series window, no substitutions. This is the most restrictive form and is generally only legal on private projects or when sole source is justified. Proprietary open. Provide Acme Model 3500 or approved equal. Preserves the design intent while allowing competitive bidding, which is why it dominates public work. And the practical reality on most projects? Real specifications combine all 3 types across different sections. Proprietary for the precise architectural products that matter, prescriptive for the commodities, and performance for the engineered systems the contractor builds. Walk away with these 4 takeaways and you will pick the right spec type for any condition. 5 takeaways on specification types. Prescriptive specifications give the architect maximum control over the product, but transfer the performance risk to the architect because choosing the exact product is choosing the exact performance outcome. Performance specifications let the contractor control the means, but transfer the performance risk to the contractor because the contractor is now responsible for delivering the named result. Proprietary closed specifications, no substitutions, are sole source, and on public projects they are legal only when the architect can justify sole source under the local procurement code. Otherwise, the architect's firm gets sued by a losing bidder for restraint of competition. Or approved equal language preserves competitive bidding while protecting design intent, which is why it dominates public work and why the exam expects you to recognize the phrase. And most real projects mix all 3 spec types deliberately. Proprietary, where exact products matter, prescriptive for commodities, performance for engineered systems, because no single type fits every section. Here is the drawings versus specs rule that the exam tests on every PPD attempt and that real projects fight about every week, and you must internalize it. Drawings and specifications are complementary, not redundant, and together they form the complete construction documents. The architect who duplicates information in both, putting the same dimension on the drawing and in the spec, creates a conflict opportunity that gets exploited the moment one of them is updated and the other is not. The architect who omits information from both leaves a gap the contractor fills with the cheapest interpretation. AIAA 201, Section 1.2.1, states explicitly that what is required by one is required by both, which means if the door schedule shows a fire-rated door, but the spec does not call out the rating, the contractor must still provide the rating, and vice versa. Conflicts between drawings and specs become RF is at minimum and disputes at worst. And unresolved conflicts end up as lawsuits, where the architect's documents get scrutinized line by line for ambiguity. Let me show you what belongs on the drawings and what belongs in the specs. 5 categories that divide content cleanly between drawings and specs. Drawings show location, size, shape, and spatial relationships, where the wall goes, how big the room is, how parts fit together in space. Specs describe quality, performance criteria, and standards, what the wall is made of, how well it must perform, which industry standards apply. Drawings show quantity, like how many doors, how many fixtures, how much area. Specs describe materials, products, and manufacturers, naming which doors, which fixtures, which finishes go in. Drawings show dimensions and geometry. Specs describe installation methods and workmanship, telling the contractor how to build what the drawing shows. Drawings show configuration and arrangement of assemblies. Specs describe the testing, inspection, and warranty requirements that prove the assembly meets the standard. And finally, drawings show graphic representation of the building, while specs describe the administrative procedures like submittals, shop drawings, mock-ups, and project closeout that govern how the contractor delivers the work. 5 rules govern coordination between the two. Break them, and you create the conflict you will defend later. 5 coordination rules that prevent the most common drawing versus spec lawsuit. Do not duplicate. State it once in the correct location, because every duplicated fact is a conflict waiting for one of the 2 documents to be revised. Drawings show where and how much. Specs describe what quality and how. And the architect who puts performance criteria on a drawing or geometry in a spec has confused the document roles. AIAA 201, Section 1.2.1 states that what is required by one is required by both, which means the contractor is on the hook for anything shown on the drawings or described in the specs, and the architect's omission from one document is not a defense against installing what the other shows. Do not put dimensions in specs, and do not put product names on drawings. The moment one drifts out of sync with the other, you have a conflict. And on direct conflict between drawings and specs, specs typically govern over drawings, though the controlling rule depends on the specific contract language. AIAA 201 defaults to coordination rather than naming a winner, while many owner-modified contracts explicitly name specs as the controlling document. Walk away with these 4 takeaways, and your drawing spec coordination questions resolve themselves. 4 takeaways on the drawings versus specs relationship. The 2 documents are complementary, not redundant. What is required by one is required by both, per AIAA 201, Section 1.2.1. And the contractor cannot escape an obligation simply because it appears in only one document. Drawings show where and how much. Specs describe quality and method. And the architect, who confuses the document roles, writes contradictory documents that get exploited at bid and litigated at closeout. Duplication creates conflict, and omission creates gaps. And the discipline of putting each piece of information in exactly one document is what prevents both failure modes. Specs typically govern on direct conflict, though the controlling rule depends on the specific contract. Check the contract language before answering a conflict question on the exam. And the consequence? Unresolved drawing spec conflicts end up as construction phase claims, and the architect whose documents created the conflict carries the liability when the claim is litigated. Here is the section format rule you must know on site. Every specification section follows the same 3-part structure, regardless of which master format division it lives in. Part 1 is general, administrative and procedural requirements for the section, including submittals, quality assurance, delivery and storage, and warranties. Part 2 is products, the materials, manufactured products, and equipment that get installed, including acceptable manufacturers and any fabrication or mix requirements. Part 3 is execution, how the products are installed or applied, covering preparation, installation methods, field quality control, and cleaning. Every spec section has the same 3 parts in the same order, and the exam tests whether you can identify what goes in each. A spec that puts product requirements in Part 1 or installation methods in Part 2 violates the format and tells the bidder the architect does not know how to write a spec, which is a credibility hit that can cost the firm the next job. And worse, a substitution clause in the wrong part of the section is unenforceable, and the contractor who substitutes a cheaper product wins a dispute the architect should have won. Let me walk you through the 3 parts and what goes in each. 3 parts, 3 content domains, and every spec section follows the same order. Part 1 General covers the administrative and procedural requirements for the section. Submittals like shop drawings and product data. Quality assurance like manufacturer qualifications and mock-ups. Delivery and storage requirements for the materials. And warranty terms for the installed work. If the contractor wants to know what to submit before fabrication, they look in Part 1. Part 2 Products covers the materials, manufactured products, and equipment that will physically be installed. The list of acceptable manufacturers, the material specifications, any fabrication requirements like welding or galvanizing, and any field-prepared mixes like grout or concrete. If the contractor wants to know what to buy and from whom, they look in Part 2. Part 3, Execution, covers how the products get installed or applied, site preparation, installation methods and workmanship standards, field quality control like testing and inspection, and final cleaning. If the contractor wants to know how to install what they bought, they look in Part 3. Put the wrong content in the wrong part, and the spec falls apart at the bid table. Substitution clauses are where section format meets bidding law, and where architects face license board complaints for restricting competition. 6 rules that govern substitution clauses on real projects. Or equal language allows the contractor to propose alternative products deemed equal by the architect, which preserves competitive bidding and keeps the architect from being accused of restraint of trade. No substitutions language means only the specified product is acceptable, which gives the architect maximum control, but is legal on public projects only when the architect can document why sole source is justified. Substitution requests are typically required within 10 to 14 days after bid award, because allowing late substitutions undermines the competitive bid and can trigger protest from losing bidders. The burden of proof for equivalence sits on the contractor, not the architect. The contractor must prove the proposed substitute is equal in performance, durability, and design intent, and the architect is not required to accept anything the contractor proposes. The architect evaluates substitutions against the documented design intent, and a written rejection with cited reasons protects the architect from a claim of arbitrary refusal. And public projects often require or equal language by statute to preserve competition, which is why a no substitution spec on a public project can violate procurement law and expose the firm to a losing bidder lawsuit. Walk away with these 4 takeaways, and your spec format and substitution questions resolve cleanly. 4 takeaways on section format and substitution clauses. Every spec section follows the same 3-part structure. Part 1, General. Part 2, Products. Part 3, Execution. And you must know which content lives in which part on site. Content placed in the wrong part is unenforceable at the bid table, which means a poorly organized spec turns into a dispute the contractor wins. Or equal language preserves competition and protects the architect from restraint of trade claims. No substitutions language requires documented justification, especially on public projects, or the architect's firm faces a bid protest action by a losing bidder for restricting competition. The burden of proof for any proposed substitution sits on the contractor, not on the architect. The contractor must demonstrate equivalence in performance, durability, and design intent, and the architect is fully within their rights to reject a substitute that does not meet the standard with a written rationale. And public project sole source specs can violate procurement law and trigger losing bidder lawsuits. So the architect who writes a no substitutions clause on a public project must document the justification carefully or face the resulting claim. Here is the coordination principle most architects misread until they are deposed. The architect is the lead coordinator during design development, and BIM is a tool, not a coordinator. A clash detection report does not coordinate a building. It just shows you where the conflicts are. People coordinate buildings. The architect leads the meeting, assigns the resolution, and verifies the fix in the next model run. Under AIAB 101, Article 3, the architect coordinates the design services of every consultant the architect has retained: structural, MEP, civil, landscape, specialty. The architect does not automatically coordinate consultants the owner retains directly, and that contractual line is heavily tested. A consultant the owner hires, say a separate envelope specialist, is not the architect's consultant, and the architect does not warrant their work. Confuse that line on a real project, and you have taken on liability the contract did not assign you. And the architect who unilaterally coordinates the owner's separate consultants is the architect whose firm gets sued when those consultants fail to deliver. Let me show you the coordination cadence that actually catches the conflicts before they reach CDs. 5 coordination activities that must run during design development, and the cadence the exam expects you to know. BIM coordination meetings bring all disciplines together at least bi-weekly because the model drifts between disciplines if the cadence is monthly. Clash detection review pairs the architect with MEP and structural at least monthly or at every DD milestone, focused on the spatial conflicts the BIM software has flagged since the last run. Code compliance review pairs the architect with the code consultant at DD start and completion, because the code analysis from SD must be validated against the now detailed design before CDs begin. Sustainable design review pairs the architect with the lead consultant at each DD milestone, because credit decisions made now lock in or lock out paths that cannot be added back in CDs. An envelope coordination pairs the architect with the structural engineer and the envelope consultant as wall sections develop, because the envelope to structure interface is where leaks, thermal bridges, and movement joint failures live, and catching them now is dramatically cheaper than catching them in the field. 6 deliverables anchor DD coordination. Produce them, or you have not actually coordinated. 6 concrete deliverables that demonstrate DD coordination actually happened. Coordinated floor plans. All disciplines overlaid on the same plan, so spatial relationships across structural, MEP, and architectural are verifiable to the eye. Reflected ceiling plans, with mechanical equipment, lighting, sprinklers, and ceiling grid all aligned, because the reflected ceiling plan is where the most coordination conflicts hide on real projects. Building sections, showing structural depth, plenum space, and ceiling heights all verified against the floor-to-floor dimension, so the architect can prove the systems physically fit before they are bid. Preliminary door and hardware schedule, because hardware is one of the most coordinated long lead items, and getting it wrong delays substantial completion. Updated code analysis with exiting diagrams, because exit path distances, stair widths, and occupant loads must be verified against the actual DD plan, not the SD placeholder. And lead scorecard or sustainable design checklist updated for DD system selections, because credits the team thought were locked in at SD often have to be reconfirmed against the actual product specified at DD. Walk away with these 4 takeaways and the coordination questions on the exam resolve cleanly. 4 takeaways on interdisciplinary coordination during DD. The architect is the lead coordinator during design development, not the project manager, not the contractor, not the owner. And the exam treats this as a contractual responsibility flowing from AIAB 101. B101 Article 3 limits that responsibility to consultants the architect has retained. Coordinating consultants the owner retained directly is liability the architect did not contract for, and accepting it without a written modification is taking on uncompensated risk. BIM is a tool, not a coordinator. The software identifies conflicts, but only people resolve them, and the architect who treats a clean clash detection report as proof of coordination is fooling themselves. The cadence that catches conflicts on real projects is bi-weekly coordination meetings with monthly formal clash detection runs, plus milestone code and lead reviews. And the consequence of skipping the cadence? Late coordination failures become construction phase change orders, and the architect whose DD coordination was incomplete is the architect named in the lawsuit when the owner pays the change order and seeks recovery. Here's the compliance reality the exam tests directly. Design development is the phase where code compliance strategies and sustainable design commitments lock in. The code analysis you started at SD was based on assumptions about structural type, occupancy, exiting, accessibility, and fire protection. By DD, every one of those assumptions must be validated against the actual detailed design, because the plan check that follows CDs will surface every assumption that did not hold. Lead credits are even less forgiving. You cannot decide later. Daylighting credits require window sizes and locations that exist at DD. Energy credits require an energy model with the actual envelope and MEP selections. Materials credits require product decisions that get specified at DD, not at CDs. The architect who defers code verification to CDs is the architect explaining the redesign cost to the owner. The architect who defers lead documentation to CDs is the architect who loses credits the building has already paid for in design fees, and the owner sues for breach of the lead commitment in the contract. Let me walk you through 5 code items the DD phase must verify. 5 code items that must move from SD assumption to DD verification. Construction type was selected at SD based on area, height, and intended occupancy. But the DD drawings must verify the construction type against the actual structural system and the finishes specified, because a Type 2B selection at SD becomes a code violation if the DD drawings show combustible interior elements that push it to Type 3. Occupancy classification was determined from the program at SD, but the DD detailed room layouts must confirm the classification. A space programmed as office becomes an assembly if it includes seating for 50+ people. Egress design at SD had preliminary exit locations, but DD requires calculated travel distances, computed stair widths based on occupant load, and verified occupant load factors per the IBC. Accessibility at SD was a general compliance intent. At DD, you must verify door clear widths, restroom maneuvering clearances, and ramp slopes against ADA and AN SIA 117.1. And fire protection had a system type selected at SD: wet pipe sprinkler, dry pipe, foam. But DD must coordinate the sprinkler layout with the actual ceiling plan, the obstruction pattern, and the hazard classification of the spaces. Lead documentation at DD is what locks in or loses every credit on the scorecard. 6 lead documentation deliverables that lock in or lose credits at DD. The energy model, based on DD envelope and MEP selections, not SD placeholders, is the basis for energy and atmosphere credits, and the model must match the building actually being designed, or the credits do not survive review. Daylighting studies with actual window sizes and locations, because the daylighting credit requires verifiable percentages of regularly occupied area achieving target illuminance levels, and you cannot do those studies on a building whose windows are still placeholders. Water fixture selections and estimated water use calculations, because water efficiency credits depend on the actual flow rates of the fixtures specified in the DD documents. Materials credit tracking for regional content and recycled content, because the credits require product selections that get made at DD, not at CDs. Indoor air quality strategies. Ventilation rates that meet ASHRAE 62.1, low VOC product selections must be confirmed at DD against the actual specifications. And site credits for stormwater management and heat island reduction must be verified against the DD site plan, because changes to the site plan at CDs can quietly invalidate credits the owner is counting on. Walk away with these 4 takeaways, and your DD compliance work will hold up to plan check and lead review. 4 takeaways on code and sustainable design compliance at DD. The SD code analysis was assumption-based. The DD code analysis must be verified against the now detailed design because plan check will catch every assumption that did not hold. Lead credits cannot be deferred. DD is the phase that locks them in, and the architect who pushes credit decisions to CDs loses credits the design fees already paid for, and the owner sues for breach of the lead commitment in the contract. Egress design, accessibility, and fire protection all require DD math. Travel distances calculated, occupant loads computed, door widths verified, sprinkler layouts coordinated, not the SD placeholders carried forward. The energy model must use the actual DD envelope and MEP selections, not the SD assumptions, or the modeled performance diverges from the built performance and the energy and atmosphere credits do not survive review. And the consequence of deferring compliance work: CD phase rework, permit application denial, or lead certification failure, all of which fall on the architect when the owner asks why the project did not deliver what the architect promised. Here is the quality control reality the exam tests, and the reality that decides whether you make or lose money for your firm on real projects. QC catches errors in the deliverable, and QA prevents errors from occurring in the first place. They are not interchangeable terms. A firm with strong QA, standards, templates, training, checklists, peer review culture, needs less QC because the process makes fewer mistakes from the start. A firm with weak QA leans heavily on QC reviews at the end of every phase to catch errors that the process let through, and that pattern is more expensive, less reliable, and exhausting. Quality control during DD is the architect's responsibility, and a missed QC review at DD is the error that becomes a construction phase change order, and, if the error harms occupants, a personal liability lawsuit. The most effective single QC review on a real project is the simultaneous spec and drawing cross-check at DD completion. Reviewing them in isolation misses the most common error, which is the drawing showing one product while the spec names another. Let me walk you through the 6 QC methods that actually catch the most errors at DD. 5 QC methods that catch the most errors at DD, in roughly the order they run. Redline review puts senior staff in front of the drawings at every DD milestone with a red pen, looking for errors the production team missed, and the value depends entirely on the reviewer's experience, because a junior reviewer finds typos, while a senior reviewer finds the missing fire-rated door schedule. Overlay check prints the disciplines on transparent media and stacks them physically to find conflicts, which is a low-tech approach that still catches things BIM misses, especially at the dimensional level. BIM clash detection runs continuously during DD, identifying spatial conflicts between disciplines automatically. But remember that the software flags the conflict, and people must still resolve it. Specification cross-reference at DD completion verifies that the specs reference the correct drawing details and that drawing callouts cite the correct spec sections, and this is empirically the highest yield single review on most projects. An independent peer review on large or complex projects brings an outside reviewer to examine the design with fresh eyes, which is the only way to catch errors the project team has gone blind to. A separate code compliance checklist at DD start and end runs through IBC, ADA, ANSI, and the Energy Code to confirm nothing has drifted out of compliance. QA versus QC is the exam-tested distinction that separates the strong firms from the weak ones. 5 paired contrasts that lock the QA versus QC distinction in your head. QA focuses on the process, how the firm produces work, while QC focuses on the product, the specific deliverable for this project. QA is preventive, designed to avoid errors by building good habits and good systems into how every project runs. QC is detective, catching errors after they exist in a deliverable. QA examples include firm-wide standards, training programs, drawing templates, and standardized spec sections. QC examples include redline reviews, clash detection runs, and code compliance checklists. QA builds firm-wide capability that pays off on every project the firm does. QC catches errors in this specific deliverable, and the catch does not transfer to the next project unless QA captures the lesson. And the financial reality. QA investment compounds across projects. Every project benefits from the standards, templates, and trained staff, while QC cost recurs on every project because every deliverable needs its own review cycle. The firm with strong QA spends less on QC because fewer errors get through. The firm with weak QA spends heavily on QC and still ships errors. The exam expects you to recognize that pattern. Walk away with these 4 takeaways, and your QA versus QC answers come quickly. 4 takeaways on quality control and quality assurance. QC catches the error in this deliverable. QA prevents the error from occurring through firm-wide process and standards. And the exam will hand you a question that tests whether you can distinguish process improvement from product review. Strong QA reduces QC burden because fewer errors reach the deliverable stage to be caught, and firms that invest in QA ship cleaner work with less rework cost. The highest yield single QC review on most projects is the spec and drawing cross-check at DD completion, because the most common error class is mismatched product references between the 2 documents. Independent peer review is warranted on large or complex projects, because the project team has gone blind to its own work, and an outside reviewer catches errors the team cannot see. And the consequence of skipping DDQC? The error survives to construction, becomes a change order, and if the error contributes to an occupant injury or building failure, becomes the personal liability lawsuit the architect's insurance carrier defends for years. If you remember one thing about design development, remember that it is not a polish phase. It is the moment 2-dimensional drawings collide with 3-dimensional reality. The party you sketched in schematic design freezes into a fixed armature. The engineering disciplines bring their systems into the same set of pages. The cost estimator hardened the number against a budget, and code review begins in earnest. The architect who runs the integration rhythm, frozen party, hardened cost, coordinated systems, complementary documents, is the architect whose design intent survives into construction. The architect who treats DD as polish finds out at bid that the systems do not align, the budget does not fit, and the documents leak coordination errors into every RFI the contractor will write. The exam tests whether you understand the rhythm. Practice tests whether you can run it. The SD to DD transition itself is the starting point. The party freezes, and the cost modeling method shifts at the same moment. 3 decisions anchor the start of the integration phase. The SD to DD transition is the moment when the massing and the party freeze. They stop being negotiable creative options and become the fixed armature every other discipline coordinates against. And the dimensions, materials, and systems start getting committed in detail. The cost modeling method shifts as the documents harden. Parametric and cost per square foot estimating works at the start of DD because the documents are not detailed enough for anything else. Then, quantity takeoff replaces it as drawings and specs reach a level where each scope can be measured directly. And the soft versus hard cost split is the discipline the architect protects on behalf of the client. Hard costs are everything paid to the contractor for construction. Soft costs include design fees, permits, FF&E, financing, and contingencies. And both have to be tracked together because the project budget is the sum, not just the construction number. Value engineering and constructability decide whether the design intent survives the integration phase, and timing is everything. 3 decisions decide whether the design intent survives into construction. Value engineering done right is an early phase exploration of alternatives, where the architect, the contractor, and the engineering consultants sit down before commitments harden and identify substitutions that deliver the same performance at lower cost while preserving the design intent. This is VE as a tool, and it strengthens the project. Value engineering done wrong is the same activity at bid day, where the cost overrun forces last-minute substitutions that strip features the design depends on. This is VE as a rescue, and it erodes the project because every party has already optimized around the original program, and the late changes ripple through every coordination decision. And constructability review is the contractor-led check that the documents can actually be built. Sequence, tolerance, access for trades, temporary supports, and the review catches the practical issues a designer cannot see from the drawing alone. Specifications and quality control review close the foundational arc, the documents and reviews that hold the integrated design together. 3 tools hold the documents together at the close of the foundational arc. The CSI MasterFormat is the 50-division structure that organizes the project manual. Division 3 is concrete, Division 9 is finishes, Division 23 is HVAC, and the consistent structure means every contractor, every product representative, and every plan reviewer finds the requirements they need in the same place every project. Drawings versus specifications is the documentation pair. Drawings show extent and configuration with dimensions and geometry. Specifications state quality and procedure with material standards and installation requirements, and the 2 documents are complementary rather than redundant. A fact stated in one usually does not get repeated in the other. And quality control review is the discipline that catches the integration errors before they propagate. Coordination cross-checks between disciplines, code review against IBC and accessibility, and discipline-level peer review all happen during DD, because catching the error at this phase is cheap, and catching it in construction documents is expensive. 4 takeaways close the foundational arc into the integration rhythm the design development phase asks the architect to run. Take away from the foundational arc the integration rhythm itself, rather than a list of facts. The party freeze at the SD to DD transition turns the massing and the underlying design intent from negotiable creative options into the fixed armature that structural engineers can size against, mechanical engineers can route against, and the envelope can be detailed against. The cost modeling cadence shifts as the documents harden. Parametric and per square foot estimating is the right tool early in DD, then quantity takeoff takes over as drawings and specs reach a level where each scope can be measured directly, so the budget hardens at the pace the documents do. The value engineering window lives in the early phase conversation that explores alternatives before commitments harden. VE dies as a useful tool the moment it becomes a bid day rescue. So your discipline is to schedule the VE conversation deliberately rather than wait for the cost shock that forces it. And the documentation discipline pairs complementary drawings and specifications organized by the CSI MasterFormat structure with quality control review during DD, the cheap insurance that catches coordination errors before they propagate into construction documents and then into RFIs on site. Hold the rhythm. The design intent makes the journey.